What's up, lab rats? Back in the lab, back at the bench with a board that may look familiar to some of you if you follow the channel. This is a Thermo Sorvall Legend XTR Centrifuge board. I've done a couple of videos on repairing these, and it looks like this will be another one. Just a little bit of background on this board. It's been triggering an E16 error. This happened a month or so ago. E16 is for a short across the temp sensor, which is a bit odd. You're usually not going to see that. And actually, what happened is these type of edge card connectors, they can get loose, and this one was definitely getting loose, and it was starting to become skewed on the two contacts for this sensor, and they would get shorted and triggered the E16. Refit it the first time, worked fine, and then today triggered the error again. And so this time I thought, why not just solder it in place? Not going to replace the sensor just for that. These sensors are pretty expensive, and it's like just going to solder it in. I mean, it's easy enough to pop out with the sensor connected. Doesn't really make servicing this much more difficult, so I thought, why not? I did that. It cleared the error, reassembled the unit, did a test cycle, walked away, came back to it, and the instrument was off. Would not power on. It definitely appeared that something happened on this board. I don't know how just soldering in a sensor could have caused anything, but maybe this is something I caused. So anyway, we're going to take a look at, we're going to try to troubleshoot this. All right, so why don't we go over the topology of this board real quick. I don't know if I've ever done that in detail, but let's start over here where you have mains voltage going in. Of course, this is your main power switch, and then that mains connects to the board via this connector here, and then from there it goes to a number of different paths. You've got a transformer here that is providing one of the power rails on this board. This is going to be providing the 15 volt rail reference to the primary, which is involved in the frequency converter circuit. It is being rectified by a little bridge rectifier right here, and then that 15 volts is being set by an LM317 right there. This bridge rectifier is then taking mains voltage and rectifying it and getting smoothed by this capacitor for the 24 volt rail, which is being stepped down from mains via this transformer, and then converted to DC via this AC-DC converter underneath this heatsink, and that 24 volts gets stepped down further by a step down regulator right here to 5 volts. Okay, and so you have some capacitors here, this guy, and this guy, that are involved in smoothing out the 24 and 5 volt rails. One quick note I will say about this rail in particular, I've seen a couple of hiccuping main boards from XTRs. The cause generally, at least in my experience, has always been due to a failing V21, which is a Zener diode that sets the 24 volt rail output. All right, so this Zener starts to go bad. That also interrupts the feedback circuit in this switch mode configuration, and this file start hiccuping. If that ever happens, this is always I would definitely check that first. Let's move back over to here. So, as I was saying, there is the mains voltage takes on a few different paths, and I've already explained two of them, but you also have the circuitry for the DC link, which is for the DC bus for the motor. So that is activated by this mini contactor right here, which can be activated when you shut the lid. So this guy will allow mains voltage to pass to the boost converter, which is basically in this area right here. You've got a bridge rectifier for the boost converter here. You have the boost converter diodes and or diode right here, and then this is a dual package with two transistors for the boost converter MOSFETs. Got your resonator right here, this big inductor there. This relay and this resistor or PTC resistor are just acting to limit inrush current when charging the DC link capacitors, which are these two guys right here. This is your three-phase inverter. So you've got your high and low side transistors, so 6 total. This guy right here is a digital temp sensor IC, which tracks the temperature of this heatsink, making sure that the board doesn't get, the inverter's not getting too hot. You've got your brake resistor right here and chopper circuitry over here. And let's see, I mean, you've got relays down here for driving the compressor, the condenser fan, the solenoid switch in the refrigeration system. Relays over here for the lid locks, which attach here. You've got your motor driver ICs for the lid locks. So yeah, anyway, I think I've gone over, oh, and then of course you've got the microcontroller that's running the whole show. I think I've gone into maybe too much detail on how these work, but we're going to start by checking the voltage rails, and we'll see what we can find. Okay, so the first thing that I want to check is make sure that we're getting mains voltage that to the 24 volt and 5 volt rails. Those are the ones I'm most interested in. So let's power this guy on and make sure that we have our rectified mains voltage from that bridge rectifier over here. All right, and so we do indeed have our voltage is being rectified. All right, so why don't we check to make sure we have the 24 volt rail? And so I'm going to be focusing on that step down regulator by those electrolytics. And so let's check for the 24 volt rail, make sure we have that. And so what we can do is probe. This is this step down. You guys can't really see it because it's being blocked by this capacitor, but it's D6, okay? And so we're going to probe pins 4 for ground and 8 for the input, and see what we get. Oh, so you can see we've got 25.8 volts. So our 24 volt rail is good. So let's check the 5 volt rail now. And so that's pin 7 of this step down regulator, by the way. And so you can probe pin 7, but you can also easily reach capacitor C. Is that C22 right by it? And we do not have 5 volts. We are at 0.25 volts. So our 5 volt rail is very low, and that explains a lot. Now we need to figure out why it is low. Okay, so let's check something here really quick. This regulator does have a some current limit protection or overcurrent protection to handle short circuits. If the voltage on the feedback pin falls below 0.5 volts, that will be activated. So let's check that pin, which is pin 5. And so that is very low. So I would imagine that, you know, this guy's currently performing some current limiting. So there's got to be a short circuit. It looks like. Let's turn this guy off. Do some take some resistance measurements. Let's check the 5 volt rail. And wow, look at that. It looks like we have a dead short. on the 5-volt rail. You don't get much shorter than that. With that IC, that step-down regulator, performing some current limiting, I don't know if we'll see anything getting hot if we look at everything with a thermal camera, but it's worth a try. So why don't we do that? We'll pull up the thermal camera and see if there's anything on this board getting too hot to help point us in the right direction. Wow, so we got 2 hot spots on the board, and one of them is that Zener diode. That's what I'm looking at right now. The other is another diode that is on the across the 5-volt rail, I believe. And now that I look at this, I don't know if this just happened, or because I do not recall this diode looking like this, but you can clearly see it's it looks burnt and damaged. So yeah, I'm gonna shut this guy off. But I think what we're gonna have to do is let's remove both of these. I know I have the Zener in stock. Other than that, not really seeing any hot spots. Yeah, so again, you can't really make it out, but under the correct lighting, this guy's clearly burnt right down the middle. So that was the one hot spot, this V21. And then this diode right here, which is V20, also getting very hot. So I'm going to remove both of these. So that's that guy. See if our short has gone away. Nope. Yeah, I didn't think so. That's a pretty beefy diode, but yeah. So we're gonna have to tackle this another way. While we're here, I can remove V21 as well. Wow, so I found the problem, and unfortunately I removed it off camera. But if you see this little SMD capacitor right there, it's C88. There was a little glob of solder across the cap causing that short. And of course, it is right next to the area I was soldering. So I did cause this problem. Yep. Right there. Right across that cap. So, yeah. And just to validate that, I have the board hooked up to my DC power supply right where that diode was. And we can power it on. Yep, so you can see the unit has booted up. We got our LED back, RPM, speed LED, and the microcontroller MCU is upset because clearly it's throwing some errors because of all the peripherals have been detached. So yeah, that was it. So what we're going to do is replace that Zener diode Z21 and then put back that large diode V20, and we'll pop it back in the unit, and hopefully all is well. Alright, let's see if this works. Got our diode, our Zener soldered in, and then our other diode V20 is back in, so this thing should power up. We should have our 5-volt rail back, all our power rails back. So far so good. Oh, no. Oh no, something happened. I thought we were good, but... So, this is interesting. It works when I power it via external supply. Um, it's not drawing that much current at 5 volts, so... But when we try to power it up normally, that Zener is getting way too hot still, and it won't power the 5-volt rail. So I'm not sure what's going on. Perhaps our regulator is damaged, or step down regulator, or something else, but we're not in the clear yet, unfortunately. Alright, so I've got the original step down regulator from the main board set up on a breadboard, basically simulated the circuit in the schematic. So almost everything is identical, except the inductor is a little bit larger than the one. It's 100 microfarads versus 47. That's the only one I had on hand. But if this thing is working, it should give us an output of 5 volts, or actually 5.2 volts, given the voltage divider, which sets the output. So let's power this thing on. I'll show you guys what it's doing. We're injecting 24 volts from an external supply, and we've got a meter hooked up to the output. Oh, well, actually, so this is the, right now I'm probing the feedback, V feedback pin, and you can see it's now, the regulator has disabled the output, but you noticed it was at 0.2 volts. And if we look at this schematic, I mean the data sheet for this chip, which I will embed, at 0.2 volts, the off time of the duty cycle is increased by a factor of 8 when it's less than 0.25 volts at the feedback pin. And that's for a short circuit, a short on the output to help protect the device. That might be an indication that the output internally on the regulator, there's a short somewhere. There's clearly no short on this breadboard, so that would seem to indicate that there was some internal damage caused on by the short that happened on the board. So it does seem like this regulator is bad. But let me hook up the probe to the output so you guys can also see that. And so we'll fire it up again. And we're getting roughly 0.9 volts. And then it shuts down. So it seems like there is some internal damage to the regulator, and I did order a replacement. Unfortunately, they don't sell these anymore. These are now obsolete, but there is what appears to be a direct replacement. So I've ordered some of those, and that should fix our issue. Yeah, so this is the original part, and you can see it's obsolete, and then this is what appears to be a direct replacement, so this is what I'm going to order. And then we just have the data sheet here, and so this is what I was talking about during a shorted load. You know, if the feedback pin falls below 0.5 and it's at 0.2, as you guys saw, the off time becomes 8 times the test the T-set multiplier, which is set by a resistor that's tied to pin 3 to ground. So you can see it's increased by a factor of 8. And then also, this is just a capture of the startup on the output, and you can see it's a very slow ramp. So clearly something is not going right here, and it looks like you know, the overcurrent protection is trying to kick in, but it does seem like that this is for some sort of internal short on the output of the regulator. Alright, so I wanted to come back to this Zener diode, which right now I've got the board. I'm injecting 5 volts with my DC power supply to the 5-volt rail, and then the board is being powered up with my isolation transformer, so the 24-volt rail is active. And this Zener diode that sets the 24-volt rail is still getting pretty toasty at, you know, 50-55 degrees C. Not nearly as hot as it was getting. So if I shut off the 5-volt rail, and I've been monitoring it now for a little bit, temperature's staying pretty consistent. So I've just shut off the 5-volt rail. You can see it's starting to get hotter. Alright. Yeah, so what I was getting at there is that with some load applied to the 24-volt rail, with the 5-volt rail being active, it's going to be able to activate some of these relays. Relays K11 and K12, they automatically come on when you power up the board. So what I'm getting at is, without the 5-volt rail, the 24-volt rail doesn't really have much of a load on it. And so a lot of that Zener diode is going to be dissipating a lot of power. And so if we look at the through heat, and so if we look at the resistor in series with that Zener diode, measure the voltage across it. Oh, well, we should turn the board on. We're measuring roughly 1.75 volts, okay? It's a 220 ohm resistor, so 1.75 divided by 220 is roughly 8 milliamps, times the Zener voltage, which is 24 volts. You're looking at roughly 200 milliwatts that is being dissipated by that Zener diode, which is a pretty good amount for these small SOT23 components. This one in particular, I believe, is rated for 350 milliwatts and can operate up to 150 degrees C. But still, that could explain why it was getting super hot during our initial troubleshooting, and then with the 5-volt rail activated, you know, you don't see it get as hot. So, but nonetheless, these boards still seem to have a problem with these diodes, these Zeners getting way too hot. Since I've seen a couple of them fail, they seem to be a failure point. Alright, so we got our new step-down regulators in, and I popped one into the board, and the 5-volt rail is now reading 3.4, and I was like, oh boy, what else is going on here? There must be another issue. But I decided to also pop one in on our little test circuit, and I also achieved roughly 3.4, 3.5 volts. And I was like, well, that's interesting. What else is going on here? And it turns out this part, as I had mentioned, is, you know, we can't get the original anymore. It's obsolete. This A4447 has a lower reference voltage. It's not 1.2, it's 0.8. And so the V out is set by this equation. So you're going to get a lower output voltage using the same feedback resistor network. And so we're going to have to change that. Now, the data sheet doesn't give too much information. As it has this little note here that the impedance of the FB network should be kept low to improve noise immunity. Large value resistors can pick up noise generated by the inductor. So what I'm thinking is, if we go back to this, the schematic here, is we keep R37 at 10K, and then we lower R42. That's what I'm thinking. So I've written out a little equation to calculate that. Okay, so this is what we're looking at as a resistance value, about 1.82K. Sure enough, I've got something pretty close, 1.78. Or we could go with 1.96. Let's try this guy first. And we'll see how it goes. We want to have a voltage a little bit higher than 5 to compensate for the load. So we'll give that a try. Alright, so this will be the moment of truth. We replaced that resistor R42 with that 1.78K resistor. So let's power this guy on. See what happens. Yep. So we're at 5.4 volts. Might be a little high. But it worked. So it appears that that regulator saved this board. Well, the next thing to do is we're going to pop this guy back in the unit and see if it works. We'll see what happens. Alright, so this is the moment of truth. Got the board back in. Let's power it on. Oh, be helpful to plug the cord in. Oh, there it is. All right. Let's do a test cycle, see if it works. All right, it's running smoothly. Running a cycle right now. Everything looks good. Checked it for accuracy. Speed accuracy, that looks good. We'll do temperature as well. But this guy looks like it's back in business. It's braking normally. That gas spring is starting to go, so we'll have to replace that soon. But yeah, that's a wrap on this one. So I'm just gonna pop on the back panel and put it back into its place, and then that'll be it. Alright, well, as I said, that is a wrap on this guy. We got it back into its position. Quick trick, if you're moving these around, just spray some 70% ethanol on the counter, and that'll help it slide a bit. But yeah, so it's back up and running. An E16 error that should have been an easy fix that I made a lot worse just by, a sloppy solder job, which, that can happen in the field. I actually brought the solder station out here, just to make it easier. Some days I'm dealing with up to 5 or 6 different pieces of equipment to repair. And so, you know, sometimes that can come back to bite you when you're trying to speed things up. But we fixed it. It was that step down regulator, which it was gracious enough to sacrifice itself, which is awesome. So thank you for that. I mean, that could have taken out a lot more sensitive electronics on the circuits on the 5-volt rail. And the good thing about these types of issues when they pop up, when mistakes happen, is they force you to learn maybe a little bit more about whatever you're working on. Maybe you wouldn't have had to dug as deep. And so this was definitely the case here. I learned a lot about how that step-down regulator circuit works. Got to dig into the schematics a little bit more. So, you know, these don't have to be in vain when you make mistakes like this. You know, there's a number of ways you can learn from them, and I feel like I did in this case. So, anyway, this one's done. I hope you guys found this video interesting or helpful. If you have any feedback, leave it in the comments, and I'll catch you at the next repair. All right.